In this work, we present Diffuse-CLoC, a guided diffusion model for physics-based character look-ahead control. Methods for physics-based motion generation using diffusion can be broadly classified into three categories. The first one converts diffusion-generated kinematic motion into actions through RL tracking, though its success depends heavily on the motion and tracker quality. Another strategy involves modeling actions as a conditional distribution given states. This works well for physics-based tasks, but the diffusion process cannot be guided or unpainted. The third approach jointly models states and actions. While no prior methods have successfully implemented this strategy, our framework provides the first effective solution. Our framework comprises three stages. First, we obtain action labels by using a tracking policy to follow kinematic trajectories from a subset of A mass. During the expert rollout, we introduce noise into the actions to perturb the states and collect corrective behaviors. Second, we train a joint state-action diffusion model offline. Finally, for new tasks, we leverage the unconditional model's look-ahead trajectory to optimize task-specific costs through classifier guidance. During training, we randomly sample time steps for state and action denoising independently, ensuring varied noise levels across trajectories. The model learns to denoise by predicting clean trajectories through mean-squared error loss minimization. Next, during inference time conditioning, we use classifier guidance to complete novel downstream tasks. For each diffusion step, we input the noisy trajectory at step K into the model to predict both the clean trajectory and the noise. We then compute task-specific costs and gradients based on predicted states and environmental information. These gradients modify the predicted noise to determine the next denoising step's mean, from which we sample the next noisy trajectory iteratively. All demonstrations use the same pre-trained diffusion model with different guidance techniques. Using classifier guidance, our model can easily steer the character to avoid static obstacles during inference. We can extend the formulation so that the character can also avoid dynamically moving obstacles, such as other characters. Additionally, we can specify a list of waypoints and steer the character to move toward them in sequence. Our model can perform a variety of tasks by defining the problem in each task space. For example, the character can follow a predefined trajectory for its route. By specifying a sequence of target locations for a body part, the character will reach those positions using the corresponding body part. A user can easily steer the character with a joystick controller through commanding planar velocity, heading, and base height. Our model can also fill in dynamic and physically correct motions between a sparse set of target motion keyframes. We can easily compose multiple tasks and control the character to complete them all at once. For instance, the character can jump over multiple gaps or obstacles while moving forward, or perform a jump and crawl in sequence while moving. We compare the robustness and steerability of our method with a baseline. Our results show that characters controlled by our model produce less jittery motion and are more resilient when encountering external perturbations. When tasked with performing dynamic motions, our method generates the correct control signals to complete the task, while the baseline fails even with a reasonable prediction. In ablation, we find that a sufficiently long prediction horizon is critical for planning over complex environment. After a long journey, the character on the left will eventually reach its target and complete the first G. Thank you for your attention.